Hey everyone, thanks for joining us for today's event, Proactive Traffic Safety Management Empowered by Big Data. I'm John Patinos. I'm a project manager at the C2 Smart Center, which is a US DOT designated Tier 1 University Transportation Research Center tasked with leveraging recent advances in big data and technology to solve today's most pressing urban mobility challenges. A few administrative notes before we begin. The meeting is going to be recorded and uploaded to the C2 Smart Center YouTube channel with our other webinars and recorded seminars. I'd encourage you to ask as many questions as you have today for our presenter. If you have questions, comments, or suggestions about this research, you can ask at the dedicated Q&A session at the end of this presentation in one of two ways. You can either use the Q&A button at the bottom of your screen, or you can raise your hand if you'd like to speak to the presenter personally, and I can unmute you for you to ask the questions. So today, we're really happy to be joined by Dr. Kun Xie. Dr. Xie is an assistant professor in the Department of Civil and Environmental Engineering at Old Dominion University, ODU. And he received his PhD in Transportation Planning and Engineering from NYU. So he's part of the C2 Smart community. Prior to joining ODU, he worked as a lecturer in the Civil and Natural Resources Engineering Department at University of Canterbury. Also as a postdoctoral associate in the Center for Urban Science and Progress, CUSP, and the Department of Urban and Civil Engineering at NYU. Dr. Xie's research focuses on developing data-driven and technical solutions to enhance safety, efficiency, and resiliency of our transportation systems. And he's developed expertise in big data analytics, machine learning, and statistical modeling. His work is also recognized by a few different awards, such as IEEE's ITS Best Dissertation Award, the Kun Xie Milton Pekarsky Memorial Award, and the TRB Best Paper Award. Dr. Xie, we're very happy to have you here today. Why don't you get started?
Thank you, John, for your introduction. Hello, everyone. It's my great pleasure to present our work on how to use big data to empower the proactive safety management. So I've completed this work with my collaborators, Dr. Osby and Li from New York University, and my colleagues, Dr. Hong Yang from Old Dominion University. So we'll start with the background introduction. What is the global safety issue and what are the solutions we use to solve that issue? And after that, I will introduce the concept of the reactive safety management, and I'll give one example for that. And it is followed by the proactive safety management, how that can advance the traditional method, which is the reactive safety management. And after that, I will give you one example of how to use the real-world large-scale connected vehicle data to advance the proactive safety management. And I will conclude this presentation with some other relevant studies. So traffic safety has become a global public health issue in the world. And every year, there are over 1.3 million people died of traffic crashes. And you may know that or not, the crash injuries are also the leading cause of death of young people aged from 12 to 29 years old. So so there are a number of the initiatives launched to improve the road safety at both the national and international level. There are more than 40 cities in the United States have committed to Vision Zero. So Vision Zero is a plan aimed to eliminate the traffic fatalities. And the list is growing. So a lot of you may know that the New York City is also one of the Vision Zero cities. So from my perspective, there are 4 dimensions we can improve the road safety. For example, we can build safer roads. So safer roads are the roads that can forgive drivers' mistakes. So for example, we can build the median to avoid the high beam glare, to avoid the head-on collisions. And we can also add the safety barrier to prevent the vehicle from running out of the road. The second dimension is safer vehicles. So we can either use the advanced driving assistance system to help driver avoid collisions. Even when a collision happens, safer vehicles can absorb the energy of the crash and prevent the drivers and the passengers from injuries. The third dimension is safer road users. We can achieve that basically via the education and reinforcement programs. And the last dimension is safety management. This is what I want to focus on in this presentation. And the safety management involves a comprehensive method and a systematic approach to address safety issues. Some of the key tasks involve identify the high-risk locations or hotspots. Usually we start from that, and then we develop countermeasures to address the safety issues on those hotspots. And after we implement the countermeasures, we also need to evaluate the effectiveness of those countermeasures, and we can make better informed decisions later on. So in the last few decades, for the safety management, quantitative methods have been used to explore the safety-related data and to build safety models to assist informed decision-making in the safety management. So there are two types of safety management, reactive and proactive. The traditional one is a reactive one. So by referring to reactive, which means the actions are taken after the crash occurrence. So in reactive safety management, we heavily rely on the historical crash data for the safety evaluation. So we usually use the crash frequency or the crash severity to indicate how good or how safe a certain location is. And we also build safety models which are associating the contributing factors to the crash observations. And based on the safety models, we can identify the risk factors as well as the effects of those factors. And also we can use the safety models to assist some other key tasks, such as the hotspot identification and the safety effectiveness evaluation. So it can be very challenging actually to develop safety models given the variety of contributing factors and the inherent structure of the crash data. So here I will give one example. So it's from one of our previous studies. There are lots of studies investigating the proper model specification to accommodate the complex structure of the crash data, such as to account for the spatial autocorrelation, the multivariate response, and the endogeneity, etc. So in our study, we tend to model the crash frequency by severity, and we use the Manhattan as a case study. So in this map, you can see that the first map is the crash distribution for the no injury crashes. And the second one is for the minor injury. And the last one is for the major injuries. So by looking at this, those maps, so you may observe a few patterns. The first one is we can see the spatial clustering observed for each crash type. So we can see in the downtown and the midtown Manhattan, there are locations with high crash frequencies. And the neighboring sites of those hotspots, high frequency, high risk sites also have high crash frequencies. So we can observe the basically the spatial clustering for each crash type. And the second pattern is that we can observe the correlation between different types of crashes. So some sites with high no injury crashes also tend to have high minor injury and major injury crashes. So that's the second pattern we can observe. We can use the Moran-I test to evaluate whether or not the spatial autocorrelation is significant. So that's a quantitative way to do that. And we can see that from the univariate Moran-I statistical test tells us there exists spatial autocorrelation for each crash type. And the second bivariate Moran-I test tells us there is a spatial autocorrelation among each pair of the crash types. So you can see the p-values of all the tests are less than almost close to 0, so are very small. So to model the crash frequency by severity, we propose to use a multivariate conditional autoregressive model, MVCER model. And we assume the crash observation, the crash frequency for each type follow a Boson distribution with the expectation equal to lambda. And we can parameterize the lambda using a linear model. And we can assume there's an error term which follow gamma distribution. And also we assume there is a spatial effect term S that can affect the expectation of the crash. The spatial effect term S will follow a multivariate normal distribution, and we can use the W, the weight matrix, to specify the correlation weight between different sites. And the omega here can capture the correlation among different crash types. So basically the advantage of this model, first of all, is to account for the spatial autocorrelation of neighboring sites for one specific crash type. And secondly, it can capture the inherent correlation among different crash types. So those three maps shows the residuals of the MVCER model. And we also conducted the Moran-I test, and we found out the residuals are not spatially correlated anymore. So the observations of the crashes are spatially correlated, but once we apply the MCVA model, we find out the residual, the spatial autocorrelation disappeared. So we can verify that by looking at the p-values. We can have generally larger p-values, and we can see that the MVCER model can well capture the spatial dependency of the crash data. We can also use the MVCER model to identify the contributing factors to crash occurrence and also estimate their effects. For example, the Chakra ratios is found to be positively associated with the minor and the severe injury crashes. And the crash density, the road density can positively affect the PDO crash type as well as the severe crash type. So this model can provide us useful insight into the road safety management. So the MVCER model can also be used to assist the hotspot identification by estimating the potential for safety improvement. So the potential for safety improvement can be calculated by using the observed crash minus the estimated crash from the MVCER model. So I created this interactive website to show the ranking of different hotspots by different ranking criterion, and it can be a useful reference for the government to allocate the safety improvement resources. So there is one interesting finding. We find that there are many hotspots that are close to bridge and tunnels in Manhattan. There are some limitations of the reactive safety management. So first of all, it heavily relies on the crash data to indicate the safety performance. So the crash data may not always be available and usually underreported. So secondly, it takes a long time to collect sufficient crash for certain tasks, such as for hotspot identification, we need to use 3 to 5 years crash to identify those hotspots. And after implement the countermeasures, we need to wait another 3 to 5 years to evaluate how effective are our countermeasures. So it is very time consuming. And also it cannot assist the real-time development of the safety countermeasures to prevent crashes. So you cannot rely on the crash data to completely eliminate crashes. So presumably there could be some signal before the crash occurrence, and we want to find it. So is that possible to measure the crash? Is that possible to measure the safety performance without crash data? So in this video, so there is no crash observed, but you could feel this is not a safe intersection, right? So although there is no crash, but there are many near crash situations where two vehicles almost collide with each other. So we can call those near crash situations conflicts. So because there are many conflicts observed, we can know this is not a safe intersection without referring to its crash data. So we can use the conflicts as a surrogate to the crash data. Surrogate safety measures are usually used to capture the near crash scenarios or conflicts, and we can use that to evaluate the safety performance. The most widely used SSM is the time to collision. Is a TTC. Is defined as the time required for the two vehicles to collide if they continue at their present speed and on the same path. So this animation shows you one coupling scenarios, and the TTC is able to capture this type of the rear end conflict. So mathematically, TTC can be calculated by using the distance between the two vehicles divided by the speed difference. So this is a simple formula for the TTC. So if TTC is less than a certain threshold, we can say one conflict is detected. So what we want to propose is a proactive safety management. So by proactive, I mean to say the actions can be taken before the crash occurrence. So what we want to achieve is to manage the safety, just like how we manage the congestion right now. So for the congestion management, it's easy to be proactive because we can measure the congestion level in almost real time. If we know the highway is going to be congested, we can implement the ramp metering, or we can use some adaptive signal control method to prevent the congestion proactively. So when we can manage the congestion proactively, why we cannot do that for the safety, right? So the key barrier is that it's very difficult to assess the safety performance in short period of time. So this is a key barrier. But the SSM data, as I showed you previously, can have great potential to assess the safety performance in a timely manner, and thus support the proactive safety management. So for each of the tasks in the safety management, SSM data can advance it. So for example, the hotspot detection, we can, by using the assessment data, we can detect the hotspots in a short period of time without using up to 3 to 5 years crash data. And also, instead of developing the countermeasures after crash occurrence, SSM data enable active actions to prevent crashes. And lastly, we can evaluate the effectiveness of countermeasures once they are implemented. We do not need to wait another 3 to 5 years to do the safety evaluation. So this is how the SSM can potentially improve the safety management to make it more proactive. So in the area of big data, we have unprecedented opportunity to collect the SSM data from emerging data sources, such as the surveillance cameras and all the connected vehicles, the smartphone data, right? So we have many emerging data sources, and they provide us rich information for the vehicle trajectory, vehicle motion, speed, and positions. And we can extract the SSM from those vehicle motion data and use that for proactive safety management. So on the other side, there is a big advance in artificial intelligence and machine learning. So this can advance the safety analytics in 2 ways. First of all, those technologies make it easy to extract useful information from unstructured data, such as video. And secondly, it can improve the ability to predict the safety risks. So in one of the studies we conducted previously, we leveraged the video data to extract the vehicle trajectories, and we can identify the conflicts and use that for information to monitor safety performance and to predict the crash, the safety risks. So the first figure is the original video, and the second one is we use a KOT tracker to identify the key points on the vehicles, and then we cluster those critical points to identify the trajectories of the vehicles, and then we can convert the trajectory to the SSM data. So we started from the KOT tracker, but right now there is an advance in the deep learning algorithms, and that can provide us better vehicle trajectory data. So once we have the trajectory data, we can identify the TTC for each car flow in pairs. And once the TTC is less than a certain threshold, we can detect the conflict. And we have collected 70 hours video data, and we find that the conflict data is highly correlated with crash data. So we use a hidden Markov model to represent the conflict observations we assume. So they are hidden status of the safety performance, and in the low risk status, they will generate lower crash count, and in high risk status, they will generate more crash counts. So by using the HMM, we can infer the current hidden status of the traffic conditions, and we can predict what will be the likelihood that the next time interval will be at high risk status. So the hidden Markov model can help us to smooth the noisy conflict count data, so it can be used for the better safety performance monitoring. And in 2 other more recent publications, we developed a new technology, which is FDA, functional data analysis, to detect the anomaly of the traffic conditions by using the complete data. You can also check that out. So, however, the video-based safety analytics have two major shortcomings. So first one is we cannot install the camera everywhere. So the video data is only available at the fixed locations. So it's difficult to make it scalable. So secondly, the trajectory data extracted from the videos may not be accurate enough. So because the impact of the illumination variation, the camera vibration, and all the occlusion of the objects, they will all affect the vehicle tracking performance. So what we would like to propose is a more scalable and reliable solutions based on the connected vehicle data for the safety proactive analysis. So the connected vehicles, they are equipped with sensors such as the GPS, the cameras, LiDAR, radar, and those connected vehicles, they can be regarded as moving sensors in the road network. They can detect, they can collect the motion and the position data of the host vehicles as well as the surrounding vehicles. And those information can be converted into the SSM and use that to assist the risk detection and implementation of the countermeasures proactively. So the connected vehicle data we use is from the Michigan SPMD program. So, so those vehicles have, first of all, the GPS devices. So it can tell us the position and the speed, acceleration of the host vehicles. And it also has mounted mobile eye sensors. So this is computer vision-based technology. It can detect the distance between the host vehicles and the leading vehicles, as well as the speed difference between them. So if you recall the definition of the TTC, so TTC is basically the distance divided by the speed difference. So with the mobile eye data, we can calculate the TTC for each time step. So the scope of the data collection is presented here. So we have 1 month connected vehicle data, and the sample rate is 10 times per second. And the heat map on the bottom shows us where are those connected vehicles in the city of Ann Arbor. So once we have the vehicle motion data, it's also critical to use proper SSMs for the risk detections. However, the traditional SSM, such as the TTC and the DRAC, they have two limitations. The first limitation is that they can only capture the carpooling, the risk of the first carpooling scenario, when the speed of the following vehicle is higher than the leading vehicles. So as the animation shows here. But they cannot capture the risk when the speed of the following vehicle is lower or equal to the leading vehicle, as shown in the carpooling scenario 2. But is the carpooling scenario 2 absolutely safe? The answer is not really. So if the two vehicles are in close distance to each other, so if there is a disturbance on the leading vehicle, it will be prone to a collision risk. So the scenario 2 is not absolutely safe, but if we use the traditional SSM to identify the risk, we cannot identify any. So that's the first limitation of the traditional SSMs. So secondly, the traditional SSM, they are deterministic in nature. So when we are using the TTC and DRAC, we use the threshold values to capture the conflict occurrence. So if it is lower than the threshold, then we identify there's one conflict. So we use 1 to indicate the presence of conflict. So the outcome from the TTC and the DRAC will be binary. So either 1 or 0, 1 indicate 100% risky, and 0 indicate 100% safe. So what we want to propose is a new SSM that can be more, can be continuous. So it can capture the probability of the conflict occurrence between a pair of vehicles. So with a continuous outcome between the 0 and the 1. So the risk will increase continuously when the two vehicles getting closer instead of a binary outcome. So with that in mind, we propose a new SSM. So it's named as the time to collision with disturbance. So this is TTCD. So the idea is very simple. So we impose a hypothetical disturbance on the leading vehicle and assume the leading vehicles will slow down at a constant rate. And under the disturbance, it will take a certain time for the two vehicles to collide with each other. And that amount of time is measured as a TTCD. So basically TTCD is a time interval between the given of the disturbance and the collision of the two vehicles. So it's the time to collision when there is a disturbance. So this is a modification of the classical TTC. So there are two possible collision outcomes depending on the deceleration rate. Outcome 1, so the collision happens when the leading vehicle is still decelerating. So outcome 2, when the collision happens, the leading vehicle is fully stopped. So based on different collision outcomes, we can derive different formula to calculate the TTC. So I will skip the process to derive the formula for the TTCD. So if you are interested in that, you can check out our paper published in AAP. So to sum up, the TTCD can be expressed using this formula based on the value of the deceleration. So you can see that TTC is expressed as a function of the D. D is actually a random variable. It follows a certain distribution. So if D is a random variable, we can also view the TTCD as a random variable. So if we define a threshold for the TTCD, if the TTCD is less than the predefined threshold, one conflict is detected. So because the TTCD is a random variable in nature, so we can obtain the probability of the conflict. So basically, it's a probability when the TTCD is less than the threshold. So the deceleration D is definitely related with the traffic dynamics. So in different conditions, we have to choose different D. So for this study, we assume the D follows a shifted gamma distribution. You can also specify your distribution for your study based on the traffic dynamics. And the Monte Carlo method is used to calculate the probability of the conflict. So once we have the conflict data, we want to do two things. The first thing is that we want to confirm the correlation between the conflict data identified by SSM and the crash data. So that's first thing. And the second thing is that we want to fuse the crash data and the conflict data for better safety analytics. So we start with the first one. So to confirm the correlation between the SSM and the crash. So from the traditional SSM like TTC and the DIAC, they can only identify the occurrence of the conflict 0 or 1. So basically, the conflict counts. But the TTCD can give us a numeric outcome between 0 and 1. It actually tells us the probability of the conflict occurrence. So if we calculate the risk captured by different SSM for each chip, and we aggregate the chip-based risk into the location-based risk, actually the row segment-based risk, and we are investigating the risk identified by different SSMs, and how is that correlated with the crash count. But we should be aware that there is a potential confounding effect. So the confounder is the traffic exposure. So when there is a large traffic exposure, when the traffic volume is large, it's more likely to have the conflict risk, right? And meanwhile, it's also more likely to have the crash counts. So because of the confounding effect, the SSM, we cannot actually distinguish whether or not there is a true relationship between the SSM and the crash count. So we have to account for the confounding effect. So the way to do that is actually very simple. We can calculate the crash rate. We use the number of the conflicts divided by the traffic exposure and try to correlate that with the crash rate, the number of the crashes divided by the traffic exposure, right? So that's a way to account for the confounding effect. So if after account for the confounding effect, if there's still a correlation between them, then we can say, okay, they are truly related with each other. So that's what we did. And we investigate how those risks identified by different SSMs are related with the crash data. So we compared the TTC, DIAC with the TTCD. So all the three SSMs, they are subject to the selection of the thresholds, SM thresholds. So we explore how the threshold selection can affect the correlation with the crash data. And we find out we can identify the optimal threshold. So for example, for the TTCD, the optimal threshold is 1.7 seconds. So we can say that when the threshold is equal to 1.7, it can reach the maximum correlation coefficient. So this is the selection of the optimal threshold. And on the other hand, we can see that the TTCD we proposed can lead to a higher correlation coefficient compared with the TTC and the DIAC. So if we use three different SSM to identify the risk for one chip, that's how it will look like. So for the TTC and the DIAC, they can identify, okay, there are two conflicts, right, at the very beginning and at the end. But TTCD will give us a more reliable and continuous measure of the safety risk. So you can see that if we look into some of the confluence scenarios, and we find out those confluence scenarios, the leading vehicle have very close distance to the following vehicles, and they have small relative speed. The leading vehicle is not faster than the following vehicle. So that's why this type of the safety risk got neglected by the DIAC and the TTC, but got captured by the TTCD. So there are three maps here. The first one shows the crash density. Second one is a conflict density. And the last one shows the magnitude of the AADT for each highway segment. And we can see that the TTCD has great potential to infer the crash risks than the AADT. For example, for this route, the AADT is not high, but actually there are like many crashes and there are many conflicts. So the conflicts data are more related with the crash distributions. That's from our observation. So the left map shows also still shows the distribution of the crashes, and the map on the right shows the risk identified TTCD at each day in April in the same month. So our intention is to show the potential of the use the CV data connected in a short period of time to detect the risk, and we find out that's feasible. So for example, we can identify some of the high risk locations by just use the connected vehicle data in a shorter period of time. So you can see there are those two high risk locations. They also tend to have high conflicts. So the second thing we would like to do is to fuse the SSM and the crash data for the safety analytics. So because there are limitations of crash data and also the SSM data. So the limitation of the crash data, first of all, is crashes are very scarce. So the scarcity of the crash data is an issue. It takes a long time to collect sufficient crash data. And secondly, the crash data has wide variation. So if for the same site, even though there is no safety treatment, you can find out the crash observation differ greatly from year to year. So there is a wide variation of the crash data. And there are some other issues, such as the availability issue and the underreporting issue of the crash data. On the other side, the assessment data also have limitations. So for example, the SSM data are subjected to the measurement errors of the vehicle motion data, like the vehicle tracking, the computer vision-based technology. They are not perfect. They may generate measurement errors. And secondly, so there is a selection bias or sampling bias because the limited coverage of the SSM data. So we cannot select all the vehicles to obtain the SSM from them. So we can only investigate a portion of the vehicles running on the road. So there may be some selection bias. And lastly, because the improper definition of the SSM may also bring in the bias into the safety analysis. So, so both the crash and the SSM data have limitations. So we need to find a way to avoid them. So one potential solution is to fuse the SSM data and the crash data. So we propose a spatial structure equation model to do that. So this diagram is the path diagram, conceptual path diagram of the structure equation model, SEM. So it can allow us to test for the theoretical proposition using non-experimental data. So the rectangles denote the observed variables, and the ovals in the path diagram denote the latent variables. So the latent variables cannot be measured directly, but can be measured indirectly by certain indicators. So we construct a latent variable, risk status, and we use the risk status to assess the safety performance. So the risk status cannot be observed directly, but it can be indicated by the SSM and the crashes. So if the evasive actions are taken successfully, it will lead to conflicts. Otherwise, it will lead to collisions, right? So that's how we think the risk status are related with the SSM and the crashes. So the use of the latent variable, the safety status, can help us distinguish what is the systematical part and what is the measurement error of the SSM and the crash data. So we can see that in the task diagram, so the SSM is not just affected by the risk status, it's also affected by the exposure indicators. So we use different exposure indicators for the SSM. So if the SSM are all collected by the connected vehicles, so we use the GPS points of the connected vehicles to indicate the exposure. And if the crash is for all the vehicles on the road, then we use the ADT and the VMT or VMT as an indicator for the traffic exposure to the crashes. And also we assume some other road attributes like the road geometry, the pavement conditions, traffic conditions, weather, and other covariates will affect the risk status. And from the previous example, we also find that the safety performance of the sites are spatially correlated. So we cannot ignore the spatial effect. So we also assume the risk status will be affected by the spatial effect. So this spatial effect can account for the spatial unobserved factors that can affect the safety performance. So we propose to use a SEM CAR model. So this is a SEM model with consideration of the spatial effect. So there are two parts of the model. The first one is the measurement part, and the second one is the structure part. So we assume the observation. So if the observation is a counter variable, it follows a boson distribution with mean lambda, and we can formulate the lambda, and we can say that the lambda is affected by the risk status. In the structure equations, so we can assume the risk status follow a Gaussian distribution. So that's why we include the Gaussian error term here. And we use the S term to capture the spatial effect. So this is the car spatial effect term, and the S follows a normal distribution. And the sigma here is a parameter controlling the variance of the spatial autocorrelation. So this is the model specification for the SEM CAR model.
Just about time to move into the Q&A, so maybe a few more minutes on the
Okay, all right, yeah. So just very quickly, so this is the results of the SEM CAR model, and we find that all the coefficients are follow our assumptions, theoretical propositions, so you can validate this SEM model. So this shows the risk status, how the risk status are able to fuse the crash data and the SSM data. So we can see some locations with low crash counts and more complete count and some locations with more crash count and low complete count. Another work I'm working with my PhD students is that to use the connected vehicle data to identify the risky lane changing behaviors. So previously we only focus on the coupling scenarios, right? But right now we can expand that to capture the risky lane changing behaviors. So we use the autoencoder to first detect the lane changes, and then we use the two-dimension TTCD to identify the risky lane changing behavior and associate that with the crash data. All right, so I think the time is running out. I will just stop here and let me know if you have any questions.
Okay, thank you very much, Dr. Xie. The first question actually comes from Matthew Watkins. I think you mentioned this, but where is your current connected vehicle data source from? But then also, how accurate is data sourced from smartphones? Matt's understanding is that mobile data is very unreliable and inaccurate.
Okay, yeah. So it's obtained from FHWA. There's the ITS data portal. So that SPMD data is open source, so everyone is able to download that. So if you are interested in that, I can share the link to download the data. And in terms of the reliability of the data, so it's not actually smartphone data. So this is computer vision data. So it's developed by a tech company. It's called Mobileye. So it's a leading company actually in the autonomous driving. So they have very solid solutions to obtain the vehicle motion data by using the cameras.
Okay, so it looks like someone's raising their hand. So Yuan, I'm gonna allow you to talk right now. You can go for it. You can unmute and ask your.
Can you hear me?
Yeah.
Question about the past diagram. You have measured SSM and crash exposure.
Yeah.
What are they the same thing, or why do you use separate? Why do you measure them separately? I mean, the exposure of crash and the exposure of SSM.
Okay, so because the exposure for SSM and the crashes can be different. The reason is that the crashes are the crashes of all the vehicles, right? But the SSM are generated only by a sample of the vehicles. They are all only generated by the connected vehicles, right? So we have to use different exposure to indicate different the response variables. Yeah.
So how might existing onboard sensor technology, as it's currently deployed in the cars that are on the road right now, be combined with some of the methods you described and be used for proactive safety management at the agency level?
Say that again. So
the cars on the road right now, how might existing onboard sensor technology that are currently deployed in the cars that are on the road right now, how might your methods be combined with this type of sensor data?
So I think this is the same type of data set, right? So what I presented is also onboard sensors. So it's the camera and the GPS sensors, right, installed in vehicles, and they are continuously collecting the motion data and the position data of the vehicles. Is that what you're wondering, or?
Yeah, and what is needed to happen for agencies to begin to implement this technology today and use it for proactive safety monitoring? Okay,
I think the market penetration rate is still an issue right now. So we do not have many vehicles. They are well equipped with those devices. But in the near future, I would say when the connected vehicle devices become mandatory, right? So actually, most of new cars will be equipped with that device, and they are. So when we have a larger market penetration rate on the road, and eventually the agency will be able to use those rich data sets generated to make better decisions to improve the safety performance. So I believe that will happen very soon.
Okay. Matt, I'm going to allow you to talk. You can go ahead and ask your question.
John, hi. I suppose in answer to your question that you just raised to come, I mean, I'm from Wejo. You may have heard of us historically. The largest, connected vehicle data provider, globally. We have 98.9% coverage in the whole of the USA, and the average sort of penetration rate per state is always above 5%. You may have heard of an analysis and a sort of testimonial that was released recently from the Purdue University by a gentleman called Darcy Bullock, who's an advocate for Wejo. We only ever need to see 5% of connected vehicle data within each state to give you the most granular sort of accurate data to hand. And of course, that can be supplemented by other sort of data means, such as some that Kun has already mentioned. But it would be great, John and Kun, to further conversations with you both. Kun, I think we have had some dealings with you historically in the past, and also John at C2 Smart, we very much have had some great conversations around connected data and what we can actually do today. Again, I'll drop you guys, both a message and hopefully look to pencil something in by way of introduction, if that's okay.
Absolutely. Thanks for sharing that, and we love it when industry folks come to these webinars. So thanks for coming.
Thank you so much, guys. Brilliant.
Yep. Absolutely. Okay, so I think with our last few minutes, unless there are any questions, I'll just ask you, Professor Xie, what comes next for this research?
Yeah, so the work we are working on is so it's related with lane changing behaviors. So the onboard sensors is also able to detect the lateral positions, as well as the lateral speed difference between the connected vehicles and the surrounding vehicles. So previously we only focused on the carpooling scenario, so we want to expand that to a different to a different driving behaviors, and that will give us a better coverage of the crash data. So that will be the next step. And the other thing we have done is using the mobile phone data. So I think it's but this type of data doesn't actually involve the interaction between two vehicles. So it's only about the driving behavior of one vehicle without knowing how they are interact with the others. And but this one has a better coverage, so it provides higher, richer data. We can also use that to relate the crash data and the driving behaviors. So that could be the future directions here for this one. Yeah.
Okay, great. Professor Xie, thank you so much for joining us and for talking with us today. I think you're an author on a recent publication, actually, in the Journal of Accident Analysis and Prevention, authored by some of our colleagues, Di Yang, Dr. Osby, Hong Yang, and Fan Zuo.
Yes.
So participants can check that out. Some quick ending notes. If you enjoyed this webinar, definitely follow the C2 Smart Center on Twitter and LinkedIn and join our mailing list. I encourage you to reach out to Professor Xie to learn more about his research. And lastly, always feel free to reach out if there's a topic you'd like to see covered. Professor Xie, thank you so much. Participants,
thank you, John.
for coming.
Thank you, everyone.
Take care.